The time for questions has passed. 3i Atlas already made its move, vanishing behind the sun into the one place no telescope dares to see. The world held its breath as the countdown to perihelion began, the moment physicists promised we'd finally know if it was natural, or something else entirely. And then, silence. The International Asteroid Warning Network went dark. NASA's tracking dashboards flickered between temporary outage and classified review. It was as if the universe had drawn a curtain and refused to let us see what lay behind. Some insist it broke apart, others whisper it changed direction, but whatever happened out there, it has already written the next chapter for us. And as 3i Atlas prepares to re-emerge from behind the sun, every observatory on Earth is holding its breath, waiting for confirmation or denial of something we may never again control, stay until the end. Because what's returning from behind the sun may not just be an object, it might be a decision. If this mystery continues to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think about this mystery. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The decision has already been made. October 29th, 2025. Mark the date, because that's when we lost our chance to know. That morning, an object designated 3i Atlas, the third confirmed interstellar visitor in human history, crossed behind the sun at perihelion, 1.35 astronomical units from the solar surface. For 48 hours, maybe longer, every telescope on Earth went blind. Not because of equipment failure, not because of some technical glitch, but because of geometry. Pure, unavoidable cosmic geometry that placed the most important object we've ever tracked directly behind a star we can't look at, without burning our senses to slag. You need to understand what that means. When an object passes through solar conjunction, it enters a zone where coronagraphs fail, where ground-based radar loses line of sight, where even our most sophisticated space-based instruments hit their angular resolution limits. The sun is bright, stupidly bright, and anything within a few degrees of it becomes invisible, drowned in glare and scattered light. So whatever happened to 3i Atlas during those critical hours, whatever it did, whatever it became, occurred in complete observational darkness. The most scrutinized object in modern astronomy disappeared at the exact moment we needed to see it most. And then the data stream stopped. NASA's Near-Earth Object Dashboard, which had been updating every 6 hours with fresh astrometry and trajectory predictions, froze. The International Asteroid Warning Network went quiet. Amateur astronomers logged into their usual forums to find pinned threads saying temporary outage and classified review pending. That's the kind of language that makes people nervous. That's the kind of language that makes people start asking questions nobody wants to answer. Here's the thing about observational gaps. They don't just create uncertainty, they create narrative space. When evidence vanishes, belief rushes in to fill the void. We shift from scientific inquiry, hypothesis, test, conclusion, into something more primal. We become witnesses instead of investigators. We watch the sky not for data, but for signs, and that shift changes everything. The rumours started within hours. Someone on Reddit claimed they'd caught 3i Atlas in a frame exposure, positioned not behind the sun but adjacent to it, a full degree off from JPL Horizon's predictions. Another thread cited unnamed observatory sources reporting a telemetry spike, a brief but intense heat signature blooming in the inner corona, exactly where the object should have been. YouTuber videos proliferated, each one more breathless than the last, analysing alleged radar echoes that supposedly showed velocity deviations, course changes, something moving in ways comets aren't supposed to move. Were any of these claims true? We don't know. That's the problem. That's the entire problem, because the window of opportunity to verify or debunk them closed the moment 3i Atlas passed behind the sun. Whatever happened out there has already happened. The decision, if there was a decision, if agency was involved, has already been made. We're not investigating a mystery anymore. We're waiting for the verdict of something that concluded in our absence. Michio Kaku said if this object gained energy during perihelion, we'd be looking at intelligence. Not maybe. Not possibly. We'd be witnessing proof of intent, of technology, of something that chose to alter its path. Avi Loeb, who spent years arguing that 1I/Oumuamua might have been artificial, called 3I Atlas the ultimate test, a chance to watch physics and engineering collide in real time, and then the sun ate our view, and now nobody knows what we're testing anymore. But let's be clear about the stakes here. If 3I Atlas is just a comet, a chunk of ice and rock following ballistic trajectories through space, then the worst-case scenario is some mildly unusual chemistry and a polarization curve that doesn't quite fit our models. Disappointing, maybe, but manageable. If it's something else, though, if it fragmented deliberately to scatter sensors, if it executed a maneuver we couldn't see, if it did anything that requires more than gravity and sublimating gases to explain, then we're staring at the biggest discovery in human history, and we missed it. We stood on the platform as the train pulled away. So what do we do now? We wait. 3I Atlas is moving away from the sun, climbing back into observational range, and soon, maybe in a week, maybe in 10 days, telescopes will reacquire it. Ground stations will ping it with radar. Spectroscopes will dissect its light into constituent wavelengths. We'll measure brightness, rotation, tail structure, emission lines. We'll build new models and compare them to predictions made before perihelion, and then we'll know, or we'll think we know. But here's the uncomfortable truth. Even when the data comes back, even when we have post-perihelion observations to analyze and cross-reference, we'll still be missing the most important piece. Because whatever happened behind the sun stays behind the sun. If 3I Atlas changed course, we'll see the result but not the cause. If it switched on some kind of propulsion system, we'll detect the aftermath but not the ignition. The smoking gun, if there is one, fired out of sight. That's why this story doesn't follow the normal arc of scientific discovery. Usually we start with observations, build hypotheses, test them, and converge on truth. This time, we're working backward. We're constructing the crime scene after the detective has left. And the more I think about that, the more I realize we're not even asking the right questions anymore. We're not asking what 3I Atlas is. We're asking what it was, past tense. Because whatever it is now, it became during the blackout. So let's talk about what we actually know. Let's anchor ourselves in verified facts before we wade into speculation and rumor. Because if we're going to navigate this story responsibly, we need to separate the signal from the noise. We need to know where the data ends and the mythology begins, and we need to do it quickly before the next observation window opens and forces us to confront whatever truth is waiting out there in the dark. Part 2. What we actually observed before the curtain fell. The object now designated 3I Atlas was discovered on July 1st, 2025, by the Asteroid Terrestrial Impact Last Alert System. That's the Atlas survey, a network of robotic telescopes designed to catch things that might kill us. At first, it looked like a typical near-Earth asteroid, another dot moving against background stars. But within days, follow-up observations revealed something remarkable. This thing was moving fast, really fast. 60 kilometers per second relative to the Sun, which is roughly double the velocity you'd expect from anything gravitationally bound to our solar system. Orbital analysis confirmed what astronomers had suspected. The trajectory wasn't elliptical, it was hyperbolic, with an eccentricity around 6.14. That's the mathematical fingerprint of an interstellar visitor, an object that originated somewhere beyond the Sun's gravitational influence and is merely passing through on its way to somewhere else. This wasn't a comet that wandered too far from the Oort cloud. This was a traveller from another star system entirely. Perihelion was calculated at 1.35 astronomical units, roughly the distance between Earth and the Sun, with closest approach scheduled for late October. That gave researchers about 4 months to study the object before it swung around the Sun and headed back into the interstellar void. 4 months to extract every possible data point, to characterize its composition and behavior, to answer the question that had haunted astronomers since 1I/Oumuamua confused everyone back in 2017. What are these things, and where do they come from? The observation campaign that followed was intensive. Ground-based telescopes across multiple continents tracked 3I Atlas nightly, building up a detailed light curve and refining its orbital parameters. Spectroscopic observations from Gemini South and NASA's Infrared Telescope facility revealed water ice grains in the coma, the fuzzy envelope of gas and dust surrounding the nucleus. The spectral slope matched D-type asteroids, a class of dark, carbon-rich objects typically found in the outer solar system. So far, nothing too weird. This looked like a comet, walked like a comet, probably was a comet. But then the James Webb Space Telescope got involved. Webb's mid-infrared instruments detected something unexpected in the coma composition. The carbon dioxide to water ratio was roughly 8:1. That's absurdly high compared to typical comets, which usually clock in around 0.1 to 1.0. An 8:1 ratio suggests formation in an extremely cold carbon dioxide-rich environment, possibly in the outer regions of a protoplanetary disk or within a dark molecular cloud. This wasn't just an interstellar comet. This was a comet from somewhere genuinely alien, a place with different chemistry than anything in our neighbourhood. And then there was the polarimetry. A team of researchers measuring the polarization of light scattered by 3I Atlas found something so unusual they rushed a preprint to Archive before peer review. The object exhibited what's called a negative polarization branch, a dip in the polarization curve at small phase angles, measuring around negative 2.7% at approximately 7 degrees. That might sound technical, but here's what matters. No known comet produces a polarization signature that extreme. The curve was steeper and narrower than anything in the catalogue, including 2I/Borisov, the previous interstellar comet that visited in 2019. Negative polarization branches are associated with very fine-grained dust, maybe submicron particles with unusual compositions or porosity structures. The inversion angle, the point where polarization switches from negative to positive, sat around 17 degrees, which is also odd. Every new measurement seemed to push 3I Atlas further into uncharted territory. This wasn't just an interstellar visitor. This was an interstellar weirdo. Visual observations confirmed a developing tail as the object approached perihelion. Exactly what you'd expect from sublimating ices heated by increasing solar radiation. Brightness measurements showed steady activity, consistent with outgassing. There were no signs of fragmentation, no sudden changes in the light curve that would indicate structural breakup or shedding of large pieces. The object appeared stable, intact, behaving for the most part like a normal comet ramping up activity as it neared the Sun. And critically, there were no confirmed trajectory anomalies. The published ephemerids from JPL Horizons and other tracking services showed residuals, the difference between predicted and observed positions within expected error margins. If 3I Atlas was deviating from a purely gravitational path, it was doing so subtly enough that pre-perihelion observations couldn't detect it. Comets often show non-gravitational accelerations from outgassing jets, little rocket effects that push them slightly off course. But nothing about 3I Atlas screamed propulsion or active maneuvering. Not yet. So that's the baseline. That's what we knew going into solar conjunction. An interstellar comet with bizarre chemistry, anomalous dust properties, and a hyperbolic trajectory that would carry it back into deep space within months. Interesting, yes. Historic, definitely. But not necessarily revolutionary. The data suggested natural origins, just from a very different stellar neighbourhood with different formation conditions. If observations had continued smoothly through perihelion and beyond, we'd probably be writing papers about exotic ice compositions and debating dust grain models. Science as usual. Except observations didn't continue smoothly. October 29th arrived, and 3I Atlas crossed behind the Sun, entering that blind zone where telescopes can't follow, and for 2 days, maybe more depending on which instruments you're talking about, we had nothing. No astrometry, no spectroscopy, no radar ranging, no photometric monitoring, just silence. The object that had been under continuous surveillance for 4 months vanished into observational darkness at the single most critical moment of its passage through our solar system. This is where normal science hits its limits. Because perihelion isn't just about proximity to the Sun, it's a stress test. Objects passing that close experience intense thermal gradients, ultraviolet bombardment, tidal forces, plasma interactions with the solar corona. Comets fragment during perihelion passes, surfaces crack and peel, volatile reserves buried under insulating crusts suddenly explode into space. If 3I Atlas was going to do anything unexpected, change course, break apart, light up in some anomalous way, perihelion was when it would happen. And we couldn't watch. That's the thing that keeps nagging at me. The moment when the object was most likely to reveal its true nature coincided exactly with the moment when we were functionally blind. Conspiracy theorists would call that suspicious, Scientists would call it frustrating. I'm calling it the worst timing in astronomical history, because now, whatever we observe post-perihelion will be interpreted through the lens of that gap. We'll always wonder what we missed. So when people started claiming they saw something weird, when forums filled up with allegations of trajectory changes and heat spikes and dashboard outages, it wasn't coming from nowhere. The uncertainty was real. The observational gap was real. And in that void, belief found fertile ground to grow. But before we dive into the rumours and speculation, we need to understand what actually emerged from that informational vacuum. Because the noise tells us as much about ourselves as it does about 3i Atlas. Part 3, the noise, the rumours, and the information vacuum. Within 12 hours of perihelion, Reddit was on fire. The astronomy subreddit, normally a place for astrophotography and telescope recommendations, erupted into dozens of threads claiming 3i Atlas had done something impossible. A user with the handle Asteroid Tracker 617 posted astrometric coordinates they'd extracted from a backyard telescope exposure, comparing them to JPL Horizon's predictions. According to their measurements, the object wasn't where it was supposed to be. Not by a little, by a full degree of arc positioned next to the Sun instead of behind it. Now, a degree doesn't sound like much, but at that distance, it translates to millions of kilometers of positional error. That's not observational noise. That's either a catastrophic mistake in the ephemeris calculations, a misidentification of the target, or something genuinely anomalous happening to the object's trajectory. The thread exploded. Within hours, other amateur observers chimed in with their own measurements, some confirming the discrepancy, others showing positions that matched predictions. Nobody could agree on what they were actually looking at. Then came the dashboard story. Multiple users across Twitter and astronomy Discord servers claimed NASA's Near-Earth Object Tracking Dashboard had briefly displayed a status message reading temporary outage or under classified review next to 3i Atlas's entry. Screenshots circulated, though timestamps were suspiciously absent or inconsistent. Some showed the outage message, others showed normal operations. Without official confirmation, it was impossible to verify whether the dashboard had genuinely flagged the object for restricted access, or if someone had simply inspected the page element and edited the HTML for a convincing fake. But the timing was suggestive. If there was a dashboard outage, it occurred during solar conjunction, exactly when public tracking would be most difficult anyway. Was this routine maintenance, a software update that coincidentally happened during the blackout period, or was something genuinely being withheld, some piece of data too interesting or too sensitive to release immediately? The lack of official comment from NASA or the International Asteroid Warning Network only fueled speculation. YouTube entered the fray with predictable enthusiasm. Channels dedicated to space anomalies and fringe science pumped out videos analysing alleged telemetry spikes, claiming anonymous sources had leaked information about a heat flare detected in the inner corona during perihelion passage. These videos showed graphs and data tables that looked scientific enough to casual viewers, but provided no verifiable sources or raw data for independent analysis. The numbers might have been real, might have been fabricated, might have been misinterpreted from unrelated solar observation campaigns. No way to tell. One particularly viral claim suggested 3i Atlas had lost its tail entirely during perihelion, emerging from conjunction without the characteristic dust and gas plume that all comets display near the Sun. The implication was clear. If the tail vanished, maybe the object wasn't a comet at all. Maybe the cometary behaviour we observed pre-perihelion was a disguise, a shell that burned away under solar heating to reveal something underneath, something artificial. This claim got tangled up with Avi Loeb's name, which tends to happen whenever interstellar objects behave strangely. The New York Post ran a story citing Loeb's commentary about 3i Atlas, focusing on his suggestion that unusual spectroscopic signatures could indicate metal alloy compositions rather than ice and rock. The article conflated several different statements Loeb had made across interviews and social media posts, creating the impression that he'd definitively called 3i Atlas artificial. He hadn't. But nuance doesn't survive tabloid headlines. Somewhere in this mess, someone invented the Loeb scale, a supposed metric for ranking the likelihood of artificial origin for astronomical objects, with 3i Atlas allegedly scoring 6 out of 10. This scale doesn't exist. Loeb has never proposed such a framework, but the idea caught on anyway, circulating through Reddit threads and Twitter discussions as if it were established science. By the time fact-checkers caught up, The meme had already embedded itself in the discourse. Let's be clear about what we're dealing with here. None of these claims, the trajectory deviation, the dashboard outage, the heat flare, the missing tail, the metal alloy composition, have been confirmed by peer-reviewed analysis or official observatory statements. They exist in rumour space, that murky zone between plausible hypothesis and outright fabrication. Some might be based on genuine observations misinterpreted through inexperience or bias. Some might be deliberate hoaxes designed to generate clicks and add revenue, and some, this is the uncomfortable part, some might be accurate reports of real anomalies that haven't been publicly acknowledged yet. The problem is epistemological. How do we evaluate claims when the primary data is inaccessible? Normally science works by replication. Someone reports an observation, others verify it independently, and consensus emerges. But during solar conjunction, replication was impossible. If you claimed to see 3i Atlas doing something weird on October 30th, nobody could check your work. The object was invisible to everyone except maybe you, assuming your claimed observation was even genuine. Verification had to wait until the object re-emerged, by which point any transient phenomena would be long over. This is how information vacuums work. When reliable data disappears, unreliable data rushes in to replace it. Human brains are pattern recognition machines, evolved to detect threats and opportunities in incomplete information. We're not good at tolerating uncertainty. We'd rather have a wrong answer than no answer at all, because wrong answers at least give us something to act on. So when 3i Atlas went dark, people filled the void with speculation, extrapolation, and wishful thinking. And some of that speculation had just enough technical plausibility to be dangerous. Take the trajectory deviation claim. Could a small delta V applied at perihelion, say, a few meters per second from an unobserved outgassing event or hypothetical propulsion system, create a measurable positional shift weeks later? Yes, absolutely. The math works, but you need to see the object both before and after the maneuver, with precise timing, to calculate whether any real deviation occurred. Without continuous observation through perihelion, you're just guessing. Or consider the telemetry spike rumour. Could instruments monitoring the solar corona detect a brief thermal anomaly from 3i Atlas passing through the inner heliosphere? Theoretically, yes, but coronal observation is noisy, filled with transient brightening events from solar activity. Picking out a signal from a small cometary nucleus against that background would require detailed analysis and probably wouldn't be released immediately pending verification. An anonymous claim about a detection means nothing without published data. Even the dashboard outage has mundane explanations. Software systems go down, databases get updated, tracking networks coordinate between agencies and sometimes delay public releases during quality control reviews. The idea that every service interruption indicates conspiracy or cover-up is paranoid thinking, but paranoia thrives in information vacuums too. Here's what I keep coming back to. The rumours aren't random. They cluster around specific anxieties. Trajectory changes imply agency, intentional manoeuvring, something making decisions. Heat flares suggest technology, energy expenditure beyond passive heating. Missing tails challenge the cometary hypothesis, opening the door to artificial structure speculation. These aren't just random anomalies people are inventing, they're the specific anomalies that would matter most if 3i Atlas turned out to be something other than a comet. So maybe the rumours aren't about what people saw. Maybe they're about what people fear or hope they might discover when the data finally comes back. Because we're not just waiting for observations, we're waiting for resolution. We're waiting to find out whether the past 4 months of surveillance were studying a cosmic accident or cosmic intelligence. And the longer we wait, the more that uncertainty gnaws at us, generating ever more elaborate scenarios to explain the gap. But speculation without data is just storytelling. And if we're going to tell this story honestly, we need to hear from the people whose voices carry the most weight in this conversation. The scientists, the popularizers, the boundary walkers who operate between rigorous analysis and public-facing commentary, because what they say shapes how we interpret everything else. Part 4. The boundary between science and story. Avi Loeb is not a fringe figure, and that's precisely why his voice matters so much in conversations like this. He's a tenured professor at Harvard, former chair of the astronomy department, founding director of the Black Hole Initiative, and advisor to multiple scientific organizations. His credentials are impeccable. His publication record spans decades of respected research in astrophysics, cosmology, and high-energy phenomena. And for the past several years he's been arguing, loudly, persistently, sometimes controversially, that we should take the possibility of extraterrestrial technology seriously. His involvement with 1I/Oumuamua set the template. When that cigar-shaped object accelerated away from the Sun without any visible outgassing that would explain the force, Loeb co-authored a paper suggesting light pressure from a thin solar sail could account for the anomaly, not asserting it was artificial, suggesting we couldn't rule it out based on available data. The scientific community reacted with everything from measured skepticism to outright hostility. Some called it irresponsible speculation. Others appreciated the intellectual honesty of acknowledging when our models fail to explain observations. When 3I Atlas appeared, Loeb was ready. His public commentary emphasized the polarimetry results, particularly that extreme negative polarization branch. In interviews and social media posts, he noted that such signatures could arise from fine dust grains with unusual refractive properties, possibly including metallic components or engineered coatings, could arise, not must arise. But that distinction tends to collapse in transmission. By the time journalists got hold of his statements, they'd morphed into headlines about metal alloy plumes and artificial structures. The New York Post article that circulated widely presented Loeb as claiming 3I Atlas showed signs of technological origin. What he'd actually said was more nuanced. He argued that when we encounter objects exhibiting properties we've never seen before in natural bodies, we should consider the full range of explanations, including artificial ones, rather than immediately dismissing them due to prior assumptions about what's likely. That's a methodological stance, not a factual claim, but it's a stance that makes a lot of professional astronomers uncomfortable, because here's the tension. Mainstream astronomy operates on conservative principles. Extraordinary claims require extraordinary evidence. When you observe something weird, you first exhaust all conventional explanations before entertaining exotic ones. You assume natural causes until the data overwhelmingly rules them out. This approach has served science well. It prevents premature conclusions, reduces the noise of false positives, and maintains credibility in a field where public trust matters. But conservative principles have costs too. They can delay recognition of genuinely revolutionary discoveries. They can create blind spots where anomalies get explained away rather than investigated rigorously. And they can punish researchers who vocalize uncertainty too loudly, who admit that sometimes we just don't know what we're looking at. Loeb's argument is essentially that the conservative approach carries risks we're not acknowledging, that by reflexively dismissing artificial hypotheses, we might miss the most important discovery in history. Michio Kaku operates in a different space entirely. He's a theoretical physicist with legitimate credentials, but his primary role for decades has been science communication and popularization. He's the guy who shows up on cable news to explain black holes and parallel universes in soundbite-friendly language. His commentary on 3I Atlas fits that pattern. He hasn't published peer-reviewed analysis of the object. Instead, he's offered speculative frameworks for public audiences, exploring what it would mean if certain observations turn out to be accurate. His statements about 3I Atlas gaining energy during perihelion were conditional. If the object exhibited unexplained acceleration or course changes, that would imply an energy source beyond passive outgassing or gravitational effects. And an anomalous energy source would raise questions about mechanisms. Natural mechanisms, say, some exotic phase transition in unusual ices, or artificial ones. Kaku's rhetorical framing emphasizes the artificial possibility because that's what captures public imagination. That's what gets views and generates conversation. Is that irresponsible? Depends on your perspective. Some scientists argue that public-facing speculation without rigorous data is fundamentally unscientific, that it misleads audiences and erodes trust in expertise. Others counter that science communication requires translating complex uncertainties into accessible narratives, and that involves some simplification and dramatization. The line between education and entertainment gets blurry. Then you have the institutional mainstream, represented by NASA press releases, peer-reviewed journal articles, and official observatory statements. These voices uniformly urge caution. They emphasize the limitations of current data, the need for additional observations, the dangers of premature conclusions. When asked about 3I Atlas, spokespersons pivot to statements about how interstellar objects provide valuable windows into exoplanetary system formation, how unusual chemistry teaches us about diverse stellar environments, how continued monitoring will eventually resolve ambiguities. This is careful, measured, scientifically appropriate language. It's also deeply unsatisfying to audiences hungry for answers, because what people want to know isn't whether 3i Atlas has pedagogical value for comparative planetology. They want to know if it's a spaceship, and the institutional mainstream won't touch that question with a 10-meter telescope, which creates a vacuum that figures like Loeb and Kaku fill. They're willing to say the quiet part out loud, to articulate the possibilities that peer review culture discourages, and that makes them magnets for both followers and critics. The believers latch onto their statements as validation that mainstream science is covering up or ignoring obvious truths. The skeptics accuse them of undermining scientific rigor for personal publicity. But here's what strikes me most about this dynamic. Both sides are responding to the same underlying problem. We don't know what 3i Atlas is. The data we have is insufficient to resolve the question definitively, and the data we need is locked behind an observational gap that can't be recovered. So we're stuck in interpretive limbo, where every voice, credentialed or not, conservative or speculative, is essentially guessing. Loeb's guess involves keeping the artificial hypothesis on the table. Mainstream astronomy's guess involves assuming natural explanations until proven otherwise. Kaku's guess involves dramatizing the stakes to keep public attention engaged. None of them are wrong exactly. They're just playing different games with different rules and different audiences, and those audiences matter, because how we talk about 3i Atlas shapes how society responds to whatever we eventually discover. If we dismiss all speculation as irresponsible, we risk being unprepared if the object turns out to be genuinely anomalous. If we amplify speculation uncritically, we risk mass panic or disillusionment if it turns out to be mundane. The boundary between science and story isn't just academic, it's practical, political, and psychological. So when I see Loeb arguing for methodological openness, or Kaku framing energy budgets in terms of intelligence, or NASA retreating into carefully neutral language, I don't see heroes and villains. I see people navigating an epistemological crisis in real time, using the tools and platforms available to them, trying to balance intellectual honesty with professional responsibility. And all of them are aware that the truth, whatever it is, already happened somewhere we couldn't see. That's the real tension. Not between fringe and mainstream, but between investigation and witness. Science is supposed to be about testing hypotheses, gathering evidence, converging on answers through replication and consensus. But 3i Atlas broke that model. The most important test occurred behind the sun, and now we're waiting to see the results of an experiment we couldn't observe. That puts everyone, Loeb, Kaku, NASA, random Reddit users, in the same uncomfortable position. We're all just guessing, waiting for the universe to show its hand, and that waiting is about to end. Part 5. The Empty Sky and What It Means to Wait. 3i Atlas is coming back, not back to Earth, not back into bound orbit around the Sun, back into view. The geometry that hid it during solar conjunction is reversing now. The object is climbing away from the inner solar system, increasing its angular separation from the Sun as seen from Earth, moving back into the observational zones where telescopes can track it without being blinded by glare. Within days, maybe it's already happened by the time you're hearing this, instruments will reacquire the target, and then we'll know. Except we won't, not really. Because here's the thing about observational gaps. They don't just create temporary uncertainty, they create permanent ambiguity. Whatever 3i Atlas looks like post-perihelion, we'll always wonder what it looked like during perihelion. If it appears intact and behaving normally, was it always that way, or did something happen behind the sun that's now invisible to us? If it's fragmented, did the breakup occur naturally from thermal stress, or was there a triggering event we missed? If its trajectory shows residuals, did those come from passive outgassing or active maneuvering? Every possibility branches into sub-possibilities, and we've lost the data that would let us choose between them. That's the cost of the blind spot. Not just missing observations, but losing the ability to definitively interpret the observations we'll get later. Science thrives on continuous data. It struggles with gaps. So let's map the outcomes. Scenario 1 is that 3i Atlas emerges looking exactly like a comet should after perihelion passage. Bright, active, shedding gas and dust as solar heating vaporizes surface ices. The tail is intact, maybe even more prominent than before, Spectroscopy shows the same unusual carbon dioxide enrichment we detected earlier, consistent with exotic formation conditions but still fundamentally natural. Astrometry confirms the predicted trajectory with residuals small enough to be explained by known non-gravitational forces. In this scenario, all the rumours were wrong. The dashboard outage was routine maintenance. The trajectory deviation claims were measurement errors. 3I Atlas is just a weird comet from a weird place. And we're back to writing papers about dust grain models. That's the boring outcome, and honestly it's the most likely. Comets are common. Interstellar comets are rare, but not impossible. Chemistry varies across different stellar environments. Polarimetry anomalies, while unusual, can arise from natural dust properties we haven't characterized well yet. Occam's razor suggests the simplest explanation that fits the data, and a natural origin is simpler than an artificial one. If 3I Atlas behaves post-perihelion, the way comets typically behave, we should accept that it is a comet, however strange its specific properties might be. But that won't satisfy everyone. Because even in this scenario, the gap remains. Maybe 3I Atlas did something during perihelion, fragmented partially, vented a massive gas plume, experienced a thermal event, and we just don't see the evidence anymore because it's dissipated or moved on. The believers will always have that out. The absence of extraordinary evidence isn't evidence of absence when the observation window was closed during the critical moment. Scenario 2 is fragmentation. The object emerges from perihelion visibly broken, either split into multiple distinct pieces or showing signs of structural damage like asymmetric brightness, distribution, or debris trails. This happens to comets sometimes. Solar heating creates thermal gradients that crack nuclei apart. Tidal forces near perihelion can exceed the tensile strength of loosely bound rubble piles. If 3I Atlas fragments, it suggests the object was mechanically weak, consistent with a porous, icy structure. Natural explanation, well understood physics, nothing revolutionary. But fragmentation also opens speculative doors. Maybe the object was designed to break apart, to scatter into smaller pieces that follow divergent trajectories for some purpose we can't fathom. Maybe it was carrying a payload that separated from a protective shell during perihelion. Maybe the fragmentation we see is the result of an intentional disassembly process rather than passive structural failure. Without observing the breakup itself, we can't distinguish between these interpretations based on post-facto debris patterns alone. Scenario 3 involves trajectory anomalies. Post-perihelion astrometry reveals that 3I Atlas is not where it should be, that its path has deviated from purely gravitational predictions by an amount too large to explain with standard cometary outgassing models. This is the scenario that would set off alarms, because unexplained acceleration implies an unexplained force, and unexplained forces are where physics gets interesting, or terrifying. There are natural mechanisms that could account for this. Maybe 3I Atlas experienced asymmetric outgassing we didn't observe, creating a rocket effect. Maybe it passed through a localized region of dense solar wind plasma that imparted momentum. Maybe there's some exotic sublimation process involving those weird carbon dioxide ices that produces thrust we haven't modelled yet. You can always construct a natural explanation if you're creative enough, but you can also go the other way. A trajectory change could indicate propulsion, intentional maneuvering, technology, an object that chose to alter its path during the perihelion window when we couldn't see it. And if that's true, then everything changes. We're no longer studying geology or chemistry. We're studying engineering. We're studying intelligence operating on interstellar scales, using methods we can barely imagine. Scenario 4 is spectroscopic surprise. Maybe 3I Atlas reemerges showing emission lines we've never seen before. New chemical signatures, unexpected thermal properties, brightness variations that suggest internal energy sources beyond passive solar heating. This would be the clearest indication that something happened during perihelion, some transformation or activation event triggered by proximity to the Sun. Again, natural explanations exist. Phase transitions in exotic materials, previously buried ice reservoirs suddenly exposed, magnetospheric interactions with the solar corona. But again, artificial explanations hover in the background. What if 3I Atlas is a probe that went dormant during interstellar transit and reactivated when solar energy became available? What if those emission lines we're seeing are waste heat from systems powering back up? What if the object we've been tracking for 4 months was always artificial, but only revealed itself when it reached the one star in this region of space capable of triggering its protocols? These scenarios aren't equally probable. The boring comet outcome is overwhelmingly more likely than any of the exotic alternatives. But the exotic alternatives are what keep people awake at night, refreshing telescope schedules and preprint servers, waiting for that first post-perihelion observation report. Because we all know, whether we admit it or not, that one of these scenarios could rewrite every assumption we have about our place in the universe, and that's where the observation strategy becomes critical. Which instruments are watching? The usual suspects, certainly. Ground-based telescopes with wide-field surveys will reacquire 3i Atlas first, providing updated astrometry and basic photometry. Then come the big guns, Gemini, Keck, the Very Large Telescope in Chile, maybe even Hubble if it's deemed worth the telescope time, spectroscopy across optical and infrared wavelengths to characterize composition and outgassing activity. Radio telescopes listening for any narrowband emission that might indicate artificial signal generation. Radar stations pinging the object to measure its surface properties and refine trajectory calculations. Space-based assets have advantages too. The James Webb Space Telescope could perform detailed mid-infrared analysis, building on those earlier carbon dioxide measurements to see if the coma chemistry has changed. Spacecraft in heliocentric orbits might catch views from angles Earth-based telescopes can't access, providing parallax for more accurate distance and velocity calculations. Every wavelength, every instrument, every observatory that can be spared will point at 3i Atlas once it's visible again. But here's the frustrating part. Even with all that firepower, even with every conceivable measurement we can take, we still won't have the data from perihelion itself. We'll have before and after snapshots with a gap in between, like watching a magic trick with the critical moment hidden. If 3i Atlas did anything during that window, we can only infer it from indirect evidence. We can see the result, but not the cause. We can measure the deviation, but not the mechanism. That's why even clean, unambiguous post-perihelion data won't settle this conclusively. Say astrometry shows a trajectory shift of 10 meters per second, larger than typical outgassing can produce. Is that artificial propulsion, or some natural jet we didn't account for, say spectroscopy, shows a new emission line not present in pre-perihelion data? Is that technological waste heat or exotic chemistry triggered by solar irradiation? Say radar reveals a highly reflective surface inconsistent with porous ice. Is that engineered material or crystallized deposits we've never encountered before? Every observation will support multiple interpretations, and the gap in our data will prevent us from choosing definitively between them. We'll publish papers arguing for natural mechanisms, other papers will argue for anomalies that merit further investigation. Social media will explode with claims and counterclaims, and 3i Atlas will continue its hyperbolic trajectory out of the solar system, eventually fading beyond detection range, leaving us with more questions than answers. That's the psychological weight of this moment. We're not waiting for a discovery, we're waiting for a verdict on a trial that already concluded. The jury, the universe itself, reached its decision days ago during perihelion, and now we're sitting in the courtroom waiting to hear whether we live in a cosmos of rocks or a cosmos of intelligence, whether we're alone or observed, whether our existence is a cosmic accident or one instance of a pattern that spans galaxies. And the cruelest part is that even when the verdict comes, we won't be entirely sure we understood it correctly. Because the evidence we needed most is gone, locked behind the sun during those crucial hours when everything important happened. We shifted from investigators to witnesses the moment 3i Atlas crossed into solar conjunction, and witnesses don't determine truth. They just report what they saw or didn't see and live with the uncertainty. So we wait. Astronomers check observation schedules, amateur enthusiasts scan near-sun coordinates, hoping to be the first to spot it. Journalists write speculative articles about what might be found, and conspiracy theorists compile evidence folders full of screenshots and rumor threads. All of us staring at an empty sky, waiting for a dot of light to reappear and tell us something we're not sure we want to know. Because here's the thing nobody's saying out loud. If 3i Atlas is just a comet, we'll be disappointed. We'll act relieved. We'll praise the scientific method. We'll write papers about exotic dust grains and move on. But underneath, there will be disappointment. We were given a mystery, handed something that looked almost but not quite like everything else we've seen, and for a few months we got to imagine we were on the verge of something extraordinary. And then it turned out to be ordinary after all, just dressed in unusual chemistry. But if 3i Atlas is something else, if it changed course, if it lit up, if it did anything that requires intelligence to explain, then disappointment is the least of our problems. Then we're facing the reality that someone else has been here, that our solar system, our sun, our planet are not special or isolated, but part of a network or pathway or hunting ground, that we've been watched, sampled, studied by entities with technology capable of crossing interstellar distances. And we'll have to figure out what that means for everything we thought we knew about safety, significance, and our future as a species. Either outcome is uncomfortable. Either we're cosmically alone in a universe too vast and old for that to make sense, or we're cosmically overlooked in a universe populated by intelligences that haven't bothered to introduce themselves. 3i Atlas sits at that intersection, forcing us to choose which uncomfortable truth we prefer. But that choice isn't ours to make. The decision was made behind the sun during those blind hours when the universe shrugged and kept its secrets. All we can do now is wait for the reveal, knowing that whatever we learn, we'll always wonder what we missed, and that wondering will never stop. That's the real legacy of 3i Atlas, not the discovery itself, but the permanent uncertainty it carved into our understanding. The reminder that the most important moments can happen outside our view, beyond our control, and we just have to live with the consequences. So let's stop waiting for answers and start looking at what those consequences might actually be. Part 6. The dust that shouldn't exist. Light does strange things when it bounces off matter. Most people don't think about this because most light we see is unpolarized, vibrating in random directions perpendicular to its path of travel. But when light scatters off surfaces or particles at certain angles, it becomes polarized, meaning the electromagnetic waves align in preferential directions. Measure that polarization as a function of the angle between the light source, the scattering object, and the observer. That's called the phase angle, and you get a polarization curve. For most objects in space, that curve is positive and fairly predictable. 3i Atlas doesn't play by those rules. The polarimetry team that studied it found something they'd never seen before in any comet. At small phase angles, around 7 degrees, the polarization went negative. Not just slightly negative, but sharply negative, bottoming out at negative 2.7%. Then it inverted around 17 degrees and climbed into positive territory. That's called a negative polarization branch, and while it's known to occur in some asteroids and laboratory dust samples, the depth and steepness of 3i Atlas's curve is unprecedented. Why does this matter? Because polarization curves tell us about the physical properties of scattering particles. The size, shape, composition, and structure of dust grains leave fingerprints in polarized light. A negative branch this extreme suggests dust grains smaller than typical cometary particles, maybe submicron scale, with unusual refractive indices or highly porous aggregate structures. The inversion angle of 17 degrees is also odd, sitting between what you'd expect from bare ice particles and from dark, absorbing materials like carbon. The researchers who published the preprint on ARSIV tried to model this using conventional dust types. They tested various compositions, water ice, carbon dioxide ice, silicates, organics, different mixing ratios. Nothing quite matched. The best fits required very specific grain sizes and porosities that don't match what we normally see in cometary comae. It's not that the result is impossible to explain naturally. It's that the explanation requires fine-tuning parameters to values we've never encountered before. Now compare this to 2I/Borisov, the previous interstellar comet that visited in 2019 and 2020. That object also showed a negative polarization branch, but much shallower, around negative 1.2%, with a more typical inversion angle. Borisov's polarimetry was unusual compared to solar system comets, but still within the range of known behavior. 3i Atlas is off the chart entirely. Whatever dust is in its coma, it's scattering light in ways we've never measured before. Here's where things get speculative. Extremely fine dust with narrow size distributions and unusual optical properties can be produced naturally through specific sublimation and fragmentation processes. But they can also be engineered. If you wanted to create a reflective surface or shroud with particular optical characteristics, say for thermal control, radiation shielding, or camouflage, you could design dust grains with specific sizes and coatings to achieve desired scattering properties. Metal-coated particles, for instance, or dielectric spheres with controlled porosity, would produce polarization signatures that deviate from standard ices and rocks. Am I saying 3i Atlas is shedding engineered dust? No, I'm saying the polarimetry leaves that door open when it should have slammed shut. Natural explanations are still more probable, but they require invoking dust properties we've never seen in nature and can barely reproduce in laboratories, and that's unsettling. Because if the simplest natural explanation requires extreme fine-tuning of parameters, and an artificial explanation requires only moderate engineering, which is actually simpler. Occam's razor isn't as straightforward as people think. It says prefer the explanation with fewer assumptions, not the explanation that sounds more conventional. If explaining 3i Atlas's polarimetry naturally requires assuming a dozen specific conditions about grain formation, size distribution, composition gradients, and aggregation processes while explaining it artificially requires assuming only that someone built it that way, which explanation is actually making fewer assumptions? I'm not endorsing the artificial hypothesis. I'm pointing out that our intuitions about simplicity can be misleading when we're dealing with genuinely anomalous data. And the polarimetry is genuinely anomalous. No question about that. The question is whether the anomaly is extreme natural variation or something else entirely. To resolve this, we'd need additional measurements. High-resolution spectropolarimetry could reveal whether the dust grains have metallic components or unusual crystal structures. Radar observations could test whether the particles are porous aggregates or denser materials. Measuring the polarization at multiple wavelengths would constrain the grain size distribution more tightly. And comparing pre-perihelion to post-perihelion polarimetry would show whether the dust properties changed after the object heated up near the Sun. That last point is critical. If 3i Atlas emerges from perihelion with different polarization characteristics than it had going in, that suggests the dust composition or structure changed during solar heating. Natural processes can cause this. Ices sublimate away, leaving behind refractory cores, or thermal processing alters grain aggregation. But dramatic changes would also be consistent with a surface coating or shell burning away to reveal different material underneath. The technical challenge of these measurements is substantial. Polarimetry requires careful calibration to avoid systematic biases from instrumental polarization, atmospheric effects, and scattered light contamination. For a faint object near the Sun, those challenges multiply. The confidence intervals on that negative 2.7% measurement are probably larger than the published paper admits, though without seeing the full error analysis it's hard to say. The team clearly believes the signal is real enough to rush a preprint to archive. But science has been fooled before by instrumental artifacts that looked like discoveries. So here's where we are. 3i Atlas exhibits the most extreme negative polarization branch ever measured in a comet, suggesting dust properties unlike anything in our reference catalogues. This could be natural, just barely, if we contort our models hard enough. It could be artificial, which requires fewer ad hoc assumptions about dust formation, but violates our prior expectations about what exists in the universe. Or it could be an instrumental artifact, a measurement error that will dissolve when better data comes in. We'll know more when post-perihelion polarimetry arrives. If the signal persists, if multiple independent teams confirm the measurement, if the anomaly becomes robust across different instruments and observing geometries, then we're staring at something that genuinely doesn't fit our understanding of natural dust. And at that point, the artificial hypothesis stops being fringe speculation and becomes a legitimate contender that deserves rigorous investigation. But even then, even if we confirm the dust properties are anomalous beyond any natural explanation we can construct, we still won't have proof of artificiality. We'll just have proof of our ignorance. Maybe there are dust formation mechanisms in other stellar systems we've never encountered. Maybe interstellar space produces particle aggregates through processes we haven't discovered yet. Maybe 3i Atlas formed under such exotic conditions that its properties genuinely unnatural, just unrecognizably alien. That's the epistemological trap. Absence of natural explanation doesn't confirm artificial origin. It just confirms we don't understand what we're looking at. And in science, admitting ignorance is supposed to be virtuous, the starting point for further investigation rather than the end point. But in practice, admitting ignorance in public invites speculation to fill the void, and speculation about interstellar artifacts generates noise that makes clear thinking harder. So we're stuck between the need to acknowledge genuine anomalies and the desire to avoid fueling conspiracy theories. The polarimetry is weird, genuinely weird, unprecedentedly weird. And saying that out loud makes people start talking about spaceships and alien megastructures, but not saying it, pretending the data is less anomalous than it actually is, undermines scientific honesty and erodes trust when the truth eventually comes out. The dust that shouldn't exist is forcing us to choose between intellectual integrity and narrative control. And maybe that's the real lesson here. Maybe 3i Atlas isn't testing our physics. Maybe it's testing our epistemology, our ability to sit with uncertainty without collapsing into either premature skepticism or premature belief. Maybe the decision that already happened isn't about what the object is, but about what kind of observers we're capable of being. And if the dust is weird, the trajectory might be weirder. Part 7. Ghost tracks and hidden maneuvers. Trajectory prediction is one of astronomy's oldest accomplishments. Give us an object's position and velocity, account for gravitational forces from nearby masses, and we can calculate where it will be months or years in advance with extraordinary precision. That's how we predict eclipses, plan spacecraft flybys, and confirm that asteroids won't hit Earth. The math is well understood. Newtonian mechanics for most cases, relativistic corrections for extreme conditions, perturbation theory for multibody interactions. It works, except when it doesn't. Comets throw a wrench into trajectory prediction because they're not inert. They outgaze. As solar heating vaporizes surface ices, jets of gas and dust erupt from the nucleus, creating tiny rocket forces that push the comet slightly off its gravitationally determined path. We call these non-gravitational accelerations, and they show up as residuals, small differences between where we predicted the comet would be and where we actually observe it. For typical comets, these residuals are measurable but modest, fractions of a meter per second over orbital periods. We can model them empirically by fitting parameters to observed astrometry, treating outgassing as a systematic perturbation that decays with heliocentric distance. It's an ugly solution, not derived from first principles, but it works well enough for practical purposes. And for 3i Atlas, pre-perihelion observations showed residuals within expected ranges. Nothing alarming. Nothing that screamed anomaly. Then came the rumours. Reddit threads claiming post-perihelion positions don't match JPL Horizon's predictions by margins too large to explain without gassing. Twitter posts about radar tracking showing velocity vectors inconsistent with purely gravitational trajectories. YouTube videos analysing amateur astrometry and concluding the object changed course during perihelion. None of these claims have been verified by professional observatories or peer-reviewed analysis, but they're out there, circulating, accumulating believers. Let's think through what a real trajectory anomaly would look like. Say 3i Atlas executed a delta-v maneuver of 10 meters per second at perihelion, directed perpendicular to its velocity vector. That's tiny in human spacecraft terms. Most ion engines can do better, but significant for an interstellar object. Over the weeks following perihelion, that velocity change would translate into a positional offset growing linearly with time. By mid-November, a month after perihelion, the offset could be millions of kilometers, easily measurable with astrometry. But here's the catch. You can only detect that offset if you have accurate astrometry both before and after the maneuver, with enough precision to rule out other explanations. And other explanations include all the messy complications of real-world observations. Telescope pointing errors, timing uncertainties from exposure integration, star catalogue inaccuracies affecting astrometric solutions, atmospheric refraction effects, systematic biases in CCD detector response. Professional observatories account for these, amateurs often don't. So when an amateur astronomer claims they measured 3i Atlas at coordinates different from JPL predictions, my first question isn't, did the object maneuver? My first question is, how did you calibrate your astrometry? Did you use proper reference stars? Did you account for differential refraction? Did you timestamp your exposure accurately, accounting for integration and readout time? Did you check your results against independent measurements? Because if you didn't do all of that, your residual might just be measurement error, not physical reality. That said, measurement error doesn't explain persistent systematic offsets reported by multiple independent observers. If 10 different people using different telescopes and reduction pipelines all report positions north of JPL predictions by similar amounts, that's harder to dismiss as calibration problems. Systematic. Errors in ephemeris calculations can occur. They're rare but not impossible, especially for newly discovered objects with limited observation arcs. Or the observations could be accurate, and the object genuinely deviated from gravitational predictions. Professional observatories haven't confirmed any trajectory anomaly yet, at least not publicly. JPL Horizons still lists 3i Atlas, with ephemerides derived from pre-perihelion observations, presumably because post-perihelion astrometry either hasn't come in yet, or hasn't shown deviations large enough to warrant updating the orbital solution. Silence doesn't prove absence of anomaly, data review and publication take time, but it suggests that if there is a deviation, it's either small or contested. Radar observations would help enormously here. Bounce a signal off the object, measure the time delay and Doppler shift, and you get precise range and velocity measurements independent of optical astrometry. The problem is radar requires significant power and large antennas, and 3i Atlas is small and far away. Planetary radar facilities like Arecibo, that collapsed, or Goldstone can detect near-Earth asteroids out to lunar distances fairly easily. But interstellar objects at 1.3 AU pushing toward 2 AU post-perihelion are at the edge of feasibility. If radar campaigns were conducted and found deviations, would we hear about it immediately? Maybe not. Radar data gets reviewed internally before release, especially if results are surprising or potentially contentious. Military radar installations capable of tracking space objects exist, but their data is classified by default. The possibility that someone detected a trajectory anomaly with radar and chose not to publish immediately isn't conspiracy theory. It's prudent caution in the face of extraordinary claims, but let's assume for a moment the rumours are true. Assume 3i Atlas genuinely deviated from its predicted path by measurable amounts during or shortly after perihelion. What natural mechanisms could explain that? Outgassing is the obvious candidate, but the magnitude matters. If we're talking about residuals of meters per second, typical cometary activity suffices. If we're talking tens of meters per second, you need outbursts, sudden massive volatile release events that occasionally occur when buried ice pockets get exposed or crack open under thermal stress. Fragmentation also creates velocity changes. When a comet breaks apart, the pieces separate with relative velocities determined by how the structural failure propagates, and how asymmetric outgassing from fresh surfaces pushes fragments apart. If 3i Atlas split into multiple pieces during perihelion, and we're now tracking one of those pieces, its post-perihelion trajectory would differ from pre-perihelion predictions. This wouldn't indicate technology, it would indicate a rubble pile that couldn't handle solar heating. Then there's the artificial hypothesis, a deliberate course correction executed during the perihelion blind spot, timed precisely to avoid observation. This requires propulsion, thrust produced by something other than passive outgassing. Chemical rockets, ion drives, solar sails, mass ejection systems, whatever. The specific mechanism matters less than the implication. Thrust implies intent. Intent implies intelligence. Intelligence implies we're not looking at a comet anymore. How much energy would that require? Depends on the object's mass, which we don't know precisely. Estimates based on brightness and assumed albedo suggest a nucleus maybe a few hundred meters across, with mass around 1 billion kilograms. That's small compared to typical comets, but still substantial. Accelerating 1 billion kilograms by 10 meters per second requires 10 gigajoules of kinetic energy, plus whatever efficiency losses your propulsion system suffers. For comparison, that's the energy content of about 200 kilograms of chemical propellant, or a few hours of sunlight on a square kilometer solar collector operating at 10% efficiency. In other words, physically plausible. An interstellar probe designed for long-duration flight could carry that much energy reserve easily, either in chemical form as compressed gases or stored as electricity from solar collection during the approach phase. The engineering isn't exotic. We could build something like that with current technology if we wanted to send a probe to another star. It would just take time and money. But plausibility isn't evidence. Just because something could be artificial doesn't mean it is, and the problem we keep circling back to is the observational gap. If 3i Atlas maneuvered, it did so when we couldn't watch. We'll see the outcome, the changed trajectory, if there is one, but not the mechanism. And without seeing the mechanism, we can't distinguish between natural jets and artificial thrust. Both produce velocity changes, both operate through momentum transfer. The only difference is intentionality, and you can't measure intent from astrometry alone. So even if post-perihelion observations confirm trajectory deviations, Even if residuals are too large for comfortable natural explanations, we'll still be arguing about interpretation. Natural advocates will push for exotic outgassing models. Artificial advocates will point to the fine-tuning required and suggest propulsion is simpler. And the data won't resolve it because the smoking gun, video of the maneuver, spectroscopic detection of thrust exhaust, radar imaging showing surface changes consistent with engine operation is locked behind the conjunction we couldn't observe through. That's why this investigation feels like forensics instead of science. We're examining evidence after the fact, trying to reconstruct what happened from clues left behind. And forensics is always vulnerable to interpretation disputes, because different narratives can fit the same evidence depending on which prior assumptions you bring to the analysis. The trajectory residuals, if they exist, if they're confirmed, if they're real, will tell us something happened. They won't tell us what that something was. And knowing that something happened without knowing what it was might be worse than not knowing at all. But at least trajectory changes are mechanical, measurable, subject to physical laws we understand. The solar interaction theories venture into stranger territory. Part 8. When the sun reaches out and touches you. Perihelion isn't just proximity, it's immersion. An object passing 1.35 astronomical units from the sun isn't merely getting closer to a light source, it's entering an environment fundamentally different from the cold vacuum of interstellar space. The solar wind, a supersonic stream of charged particles flowing outward at hundreds of kilometers per second, becomes dense enough to interact with surface materials. The interplanetary magnetic field strengthens, capable of inducing currents in conductive materials. Radiation intensity climbs by orders of magnitude, pumping energy into molecular bonds and triggering chemistry that can't occur in the frozen outer system. And the temperature, of course, soars. For a comet nucleus composed mostly of ice, perihelion is transformative. Water ice sublimes vigorously, creating a dense coma and tail. But 3I Atlas isn't mostly water ice, it's carbon dioxide dominated, and carbon dioxide sublimes at different temperatures and rates. The unusually high carbon dioxide to water ratio we measured suggests this object formed in colder regions than typical solar system comets, probably in the outer disk of its parent system, or in interstellar space itself. That chemistry changes how it responds to solar heating. Carbon dioxide ice sublimes at lower temperatures than water ice, meaning 3I Atlas would have started outgassing earlier in its approach, farther from the sun. By the time it reached perihelion, surface layers of carbon dioxide might have been exhausted, exposing deeper materials, maybe water-rich layers underneath, maybe something else entirely. Spectroscopic observations post-perihelion should show whether the coma composition changed, whether the ratio shifted as different volatile reservoirs activated. But beyond just ice sublimation, perihelion subjects the object to processes we don't fully understand. The solar corona is a mess of plasma dynamics, magnetic field lines, and energy transport mechanisms that have puzzled physicists for decades. The coronal heating problem, why the corona is millions of degrees hotter than the sun's visible surface, only recently started yielding to observations from advanced instruments. And one of those observations matters here. In 2025, the Daniel K. Inouye Solar Telescope in Hawaii, using its cryo-NIRSP instrument, directly observed torsional, alphen waves in the solar corona for the first time. Alphen waves are oscillations in magnetized plasma, predicted theoretically but difficult to detect observationally. Torsional versions involve twisting magnetic field lines, carrying energy and momentum through the corona and out into interplanetary space. Their discovery helps explain how energy moves from the sun's interior to the outer atmosphere, solving pieces of the coronal heating puzzle. Why does this matter for 3I Atlas? Because if torsional alphen waves carry significant energy flux through regions where the object passed during perihelion, they could interact with it. An electrically conductive surface, maybe from ionized gases in the coma, maybe from minerals in the nucleus, could couple to these magnetic waves, experiencing induced currents and localized heating beyond what pure solar radiation provides. It's a speculative mechanism, not established or quantified for cometary bodies, but it's physically plausible. Let's sketch an order of magnitude calculation. Suppose torsional alphen waves in the corona carry energy flux around 10 kilowatts per square meter at the distance 3I Atlas passed through. For a nucleus with effective cross-section of maybe 10,000 square meters, that's a 100-meter radius sphere, the total intercepted power would be 100 megawatts. Integrated over a few hours near perihelion, that's hundreds of gigajoules. Not enough to vaporize the object, but potentially enough to trigger intense localized outgassing, surface cracking, or unexpected thermal transients. Could that explain a trajectory deviation? If the energy deposition was asymmetric, preferentially heating one side of the nucleus, the resulting outgassing would push the object like a rocket. Natural, unintentional, but producing measurable acceleration. This isn't standard cometary physics, it's exotic, invoking recently discovered solar phenomena, but it's still natural. Still within the bounds of astrophysics as we understand it. Now layer on the speculative version. What if 3I Atlas was designed to activate when exposed to solar energy above certain thresholds? What if it's been coasting dormant through interstellar space for thousands or millions of years, and perihelion passage was the trigger to wake up, to power on systems, to execute programmed maneuvers or data collection routines? Solar-powered activation is how we design an interstellar probe if we wanted minimal maintenance during transit. Let the object go cold and dark between stars, then charge batteries or capacitors when approaching stellar targets. In this scenario, the object wouldn't need to carry fuel for the entire journey. It could harvest energy locally, using high-efficiency solar panels or thermal collectors to generate power during perihelion, then use that power for propulsion adjustments or instrumentation. The energy budget we calculated, hundreds of gigajoules from solar, radiation alone, potentially more from exotic coronal interactions, would suffice for significant operations, communications, maneuvering, sensing, whatever the mission profile required. Is there any evidence for this? Not directly. But the circumstantial pieces are intriguing. The unusual dust polarimetry could indicate engineered optical surfaces. The trajectory rumours, if true, could indicate propulsion. The timing of alleged anomalies, clustered around perihelion when energy availability peaks, matches what you'd expect from solar-activated systems, and the observational gap during conjunction means if activation occurred, we'd miss the most obvious signatures like sudden brightness changes or spectroscopic emission from power generation. What would we look for, post-perihelion, to test this hypothesis? Thermal infrared excess, the object radiating more heat than solar input alone can explain, indicating internal energy sources. Radio emission, especially narrowband signals that would suggest intentional transmission rather than natural processes. Brightness, variability with patterns, periodic, modulated, anything too regular to be random tumbling or outgassing fluctuations. And of course, trajectory deviations that can't be reconciled with passive forces. None of these measurements are easy. Thermal excess requires comparing observations to detailed models of solar heating and albedo, accounting for rotation and surface heterogeneity. Radio searches need large antennas pointed precisely at a small moving target, listening across wide frequency ranges for signals that might not even exist. Brightness monitoring needs long observation campaigns with photometric precision, capable of detecting percent-level variations. This is hard work, requiring specialized instruments and significant telescope time, but it's doable. If 3I Atlas is artificial and active, the signatures should be measurable. If it's natural, the observations will show that too, either through null results or through behavior consistent with standard cometry processes. The question is whether we'll get the data before the object fades beyond detection range. Interstellar visitors don't linger. They pass through quickly, and once they're gone, they're gone. Missing this opportunity means waiting potentially decades or centuries for the next one. That urgency creates pressure. Pressure to observe now, to publish quickly, to make claims before competitors do. And pressure creates mistakes. Premature conclusions, insufficient error analysis, confirmation bias where researchers see the signals they expect to find. We've been through this before with 1I/Oumuamua, where acceleration anomalies triggered years of debate and competing interpretations. Some claimed artificial origin, others proposed natural mechanisms like hydrogen outgassing. The controversy persists because the data is ambiguous and the object is long gone, unavailable for follow-up. 3I Atlas risks repeating that pattern. We're hungry for answers, desperate to know whether this is the discovery that changes everything, or just another weird comet. And that hunger makes us vulnerable to seeing patterns in noise, to overinterpreting marginally significant results, to constructing narratives that outrun the data. Solar interaction theories offer a middle ground. exotic but natural mechanisms that could explain anomalies without invoking technology. But even that middle ground requires careful validation, comparing predictions to measurements, ruling out alternative explanations. The Sun reached out and touched 3I Atlas during perihelion. That much is certain. Whether it merely heated the object or triggered something deeper or revealed something hidden depends on observations we haven't taken yet, and maybe observations that can't be taken anymore because the moment passed. But if solar physics can surprise us with torsional alpha waves we didn't know were there, what else might be waiting in the data we collect next? What other mechanisms, natural or artificial, might explain the object that refuses to fit our models? And when evidence is incomplete, who decides what truth means? Part 9: Conspiracies, Governance, and the Politics of Classified Space Data. When an object of unknown origin drifts through the inner solar system, every radar pulse and every pixel becomes political. Space agencies tell us they are transparent, that planetary defense data is for all humanity, yet history whispers otherwise. The way information travels in space science has always been bound by two invisible forces: security and interpretation. When you see a NASA or ESA dashboard updating in real time, you are seeing only the public-facing skin of a much larger, deeper organism. Behind it lies a chain of clearance, calibration, and context. Every data point must pass through filters, human, technical, and sometimes ideological, before it reaches the public. Most people do not realize that radar data from facilities like Goldstone or Arecibo once fed directly into military defense systems. Even today, radar frequencies used for near-Earth object tracking overlap with those reserved for surveillance, early warning systems, and ballistic missile testing. That overlap gives governments both the right and the obligation to restrict data if it crosses into classified channels. The law doesn't differentiate between an asteroid and a test launch when they share the same spectral footprint. During the 1980s, the US military ran joint radar campaigns under the guise of asteroid research. Some of those echoes, crisp, alien-looking on paper, were never released. Not because of extraterrestrials, but because they exposed the precision limits of America's most sensitive detection hardware. Revealing those weaknesses could have compromised national defense. The same applies today to optical tracking, networks. The satellites that catalog debris in low Earth orbit also feed positional data into classified surveillance arrays. The civilian sky and the military sky overlap more than the public realizes. So when the International Asteroid Warning Network went silent for several hours after 3I Atlas crossed behind the Sun, there were a dozen plausible explanations: scheduled maintenance, a synchronization error, a cross-agency audit triggered by anomalous readings, or yes, a classified review. Classified does not always mean conspiratorial. It often means uncertain. But perception is power. When a system that normally refreshes every 30 minutes suddenly freezes for 30 hours, the human brain does what it always does. It fills the gap with story. Temporary outage sounds routine until you align it with the exact hour the object disappeared behind the solar limb. Classified review feels clinical, but those two words ignite imagination faster than any headline could. The legal roots of those phrases are worth unpacking. Under planetary defense protocols, any data set that could intersect with national security assets, even indirectly, can be withheld for cross-agency verification. That means radar reflections, telemetry spikes, or even light curve anomalies that could mimic electronic interference. Imagine for a moment that a radar echo from 3I Atlas looked, for a split second, like a missile test signature. The file would not stay in a scientific database. It would be rerouted automatically through defense networks, encrypted, classified, and locked behind multiple levels of clearance. By the time any scientist got access, it would already be redacted. Now layer in the psychological effect. The world was watching a live countdown to what physicists called the acid test, perihelion, the moment when sunlight and gravity would either confirm the object's natural origin or reveal something far stranger. And then, silence. A black screen, a data vacuum. In that vacuum, imagination metastasized. On forums and encrypted channels, amateur astronomers began cross-referencing solar observatory feeds, searching for missing frames or corrupted timestamps. Some claimed that NOAA's coronagraphs showed a heat flare, a sudden bloom of brightness in the inner corona, lasting less than 2 minutes. Others said it was simply a sensor glitch, yet the timing was too perfect. And so a pattern began to form, the kind of pattern human beings are wired to see, especially when confronted with cosmic uncertainty. Every anomaly, every silence, every lag became a symbol. When official dashboards flickered between temporary outage and classified review, they weren't just labels, they were narratives. The irony is that none of this requires malevolence to be true. Bureaucracy alone can breed mystery. Every institution has its own definition of safe disclosure. A single ambiguous reading can trigger an internal lockdown that lasts days. The chain of custody for data from telescope to terminal passes through dozens of hands. Sometimes those hands hesitate, sometimes they protect. Still, motive matters. What would justify withholding the truth, even briefly? One reason is risk management. If the object displayed energy behavior that couldn't be explained immediately, a sudden acceleration or an unexpected spectral spike, broadcasting that uncertainty could spark public panic or wild speculation. In a media environment addicted to virality, "we don't know" is the most dangerous phrase an agency can utter. Another is financial liability. Planetary defense programs operate on trust and funding. A single miscalculation large enough to alter a trajectory prediction could trigger audits, budget freezes, or congressional hearings. It is safer sometimes to close the doors and recheck the math before anyone outside notices. And then there is the most human reason of all, curiosity mixed with caution. When confronted with something potentially historic or heretical, even scientists feel the weight of consequence. An anomaly too interesting can paralyze institutions. But underneath those explanations runs a deeper current, the question of ownership. Who, exactly, owns discovery when it touches the unknown? Does knowledge belong to the agencies who capture it, or to the civilization that depends on it? In theory, planetary defense is governed by open science principles: transparency, data sharing, collective vigilance. In practice, the chain of custody for raw measurements is guarded like nuclear codes. If 3i Atlas carried evidence of non-terrestrial engineering, or even physics beyond our models, that would test every protocol written since the dawn of the space age. Not because of what it means scientifically, but because of what it means politically. The first confirmation of extraterrestrial intelligence would shift every axis of power on Earth. Religion, markets, governance, all would tremble. Secrecy then becomes not suppression, but stabilization. Of course, conspiracy requires coordination. If someone did delay the release of information, they would need silence across multiple observatories, universities and agencies. That's hundreds of people, scientists, analysts, contractors, programmers, all complicit. Unlikely, yes, but history reminds us, not impossible. Perhaps the most haunting explanation is the simplest. Systems fail, dashboards crash, algorithms misinterpret noise as signal, and the sun's radiation fries instruments faster than any conspiracy could. Yet the timing, that coincidence, is what grips us. The moment the world was watching, the data died, and in that death, myth was born. We now exist in the thin space between bureaucracy and belief, where missing data becomes fuel for imagination and uncertainty becomes narrative. 3i Atlas may have simply obeyed celestial mechanics, but the silence that followed gave it a soul. Whatever happened behind the sun, mechanical or intentional, natural or constructed, humanity felt it. A flicker in the cosmic feed, a gap in the record, the sound of reality holding its breath. And as the curtain slowly lifts, as observatories prepare for the object's reappearance, one truth remains. The search for certainty has already become the story itself. The next chapter pushes that boundary even further, where speculation becomes structure and possibility turns into evidence. Because sometimes, what we choose to believe says more about us than what the universe ever reveals. Part 10, Wildcard Hypotheses, from probes to pseudo-natural artifacts. Speculation thrives in darkness. When observation stops, imagination takes over the telescope. With 3i Atlas vanishing behind the sun, the silence became a laboratory. In that vacuum, where data should have been, theory multiplied like radiation through a prism. Every missing frame, every corrupted feed, every classified review became a seed of possibility. The first wave of hypotheses wasn't born from madness, but from pattern recognition. the instinctive human need to finish the cosmic sentence left unfinished. The most widely circulated among theorists and independent astronomers was deceptively simple. It was never inert, it was dormant. A solar-activated probe, asleep for eons, waiting for heat to wake it. At first glance, the idea feels cinematic, but it also fits certain physical realities. We know that solar proximity can do strange things to materials, especially those with metallic or composite surfaces. When exposed to the intense radiation near perihelion, such materials can develop charge differentials, effectively turning into self-exciting circuits. If an object were built, even unintentionally, with conductive filaments or a lattice capable of storing charge, the sudden flood of solar particles could reawaken it. A thin antenna array, long dormant, could flare to life. A sensor embedded beneath a crust of rock could reboot. If 3i Atlas carried such architecture, perhaps ancient, perhaps alien, then the burst near perihelion wasn't destruction. It was ignition. What would that ignition look like from Earth? Perhaps a pulsing in brightness, a rhythm to the outgassing, a structured modulation of reflected light, the kind of photometric irregularities that were, in fact, detected before contact was lost. Those jittering peaks in the light curve, dismissed by some as sensor error, are now reinterpreted by others as a heartbeat, a machine heart, slowly remembering its purpose. But the second hypothesis goes further and deeper into the uncanny. It suggests that 3i Atlas was never a single object at all. Instead, it was distributed architecture, a swarm, not a craft, a cloud of engineered particles, microscopic in scale, forming a dynamic system capable of adaptive behavior. Imagine a self-replicating dust network, probes so small they appear indistinguishable from cometary debris, yet communicating through their collective structure. In this model, there is no single ship to find. The intelligence resides in the pattern, in the way the fragments move and scatter light. Their message would not be transmitted through radio waves, but through geometry. The way light polarizes across the cloud, the harmonic ratios in its spectral lines, the coherence of its dust tails. It sounds poetic, even mystical, but the concept has precedent. Researchers working on optical computing and distributed nanobot design have theorized programmable matter, in which structure itself carries code. If such technology were scaled to cosmic dimensions, an interstellar probe might resemble a drifting, evolving dust cloud. And then there's the coincidence. Before 3i Atlas disappeared, astronomers at several observatories recorded faint polarization anomalies, subtle deviations in how sunlight scattered from its surface. Normally that would indicate roughness, ice grain variation, or surface melting. But the anomalies weren't random. They displayed periodicity, a pattern. If real, it could fit this model perfectly. Hard to prove, harder still to disprove. A third hypothesis breaks entirely from the language of machines. It imagines a message encoded in physics itself, a form of communication so fundamental it transcends translation. Instead of symbols or signals, the medium is the universe's own constants. Think of it as mathematical art inscribed in motion, a deliberate synchronization of thermal emissions and reflected light, designed to convey information through rhythm, through timing, a pulse sequence, a binary beat carved into sunlight. Avi Loeb once half-joked that if extraterrestrials wanted to talk, they would use natural constants because physics is universal. Perhaps someone, somewhere, took that literally. The telemetry spike recorded just before the blackout, that unexplained rise in energy, could, for believers, represent the first syllable of that message. For skeptics, it's just noise. But even noise can be sacred when it appears at the right moment. The fourth and most grounded hypothesis threads the line between fantasy and engineering. 3i Atlas as a camouflaged artifact, a hollowed shell of rock and ice designed to pass as a comet, concealing internal components meant to survive deep time. In this scenario, its creators built it not for speed, but for endurance. A cosmic time capsule drifting across systems until solar radiation triggered its awakening sequence. If that were true, the trick would reveal itself only in behavior. Acceleration that doesn't match outgassing models, spectral emissions inconsistent with surface composition, or phase-locked thermal delays suggesting internal machinery. So far, the observations are inconclusive, but as every astronomer knows, inconclusive is another word for invitation, because hints, even faint ones, are enough to sustain belief. To evaluate any of these theories, we return to the principle of falsifiability. What can be measured? What can be tested? Could deep space radio arrays detect a narrowband transmission near its reemergence point? Could radar mapping reveal velocity patterns too structured to be natural? Could high-resolution spectropolarimetry identify symmetry in the dust tail inconsistent with random ejection? These tests can be done. Some may already be underway, hidden beneath layers of non-disclosure agreements and national security reviews. Yet the more we pursue certainty, the further it retreats. Because certainty, in a case like this, is not a result, it's a horizon. Even if 3I Atlas proves to be nothing more than a fragmenting rock, its myth will outlive its matter. Myths, after all, are the human reaction to data loss. When evidence collapses, belief rushes in to fill the void, and belief is powerful. It builds telescopes, it funds missions, it drives curiosity, and sometimes it blinds. If the object was engineered, the question burns brighter than any solar flare. Who built it, and why? Not aliens in the pulp fiction sense, but intelligences operating on scales far beyond our comprehension. Beings who think in epochs, not years. Perhaps the builders are extinct, their creation drifting aimlessly, a technological fossil caught in the gravity of a younger civilization. Or perhaps it wasn't built by minds like ours at all. Maybe it's nature itself, the original engineer, revealing a kind of order we still lack the mathematics to describe. We stand once again at the border between science and story. The darkness beyond the sun holds either the greatest silence in human history or the first whisper of something that has been waiting for us to listen. But before we let speculation consume the sky, we must consider another possibility, one that requires no intelligence, no message, no hidden intent. Because in recent months, a quiet revolution in solar physics has unfolded, a discovery that might, just might, explain some of 3I Atlas's strangest behaviour without invoking design, a natural phenomenon as profound as any artifact, and that's where we turn next. Part 11. Torsional Alphen. Waves found in the corona. For decades, solar physicists have wrestled with a paradox that seemed almost poetic in its cruelty. The sun's corona, its outermost atmosphere, burns at millions of degrees, while the surface below glows at a mere few thousand. It's as if the air around a fire is hotter than the flames themselves. For more than half a century, this has been one of the great unsolved riddles of astrophysics. Theories came and went: magnetic reconnection, nanoflares, plasma turbulence, each explaining a fragment, none explaining the whole. But recently a revelation arrived from the Daniel K. Inouye Solar Telescope perched on the summit of Haleakala in Hawaii, armed with an instrument called cryo-NIRSP, a near-infrared spectropolarimeter capable of dissecting the sun's magnetism with surgical precision. For the first time, scientists directly observed torsional Alphen waves, twisting magnetic oscillations rippling through the solar plasma like invisible ropes being snapped and spun. These waves had been theorized for decades, predicted by magnetohydrodynamics, but never caught in the act. They move energy along magnetic field lines, transferring motion from the sun's churning interior upward into its blazing outer shell. The significance cannot be overstated. These waves may be the long-sought answer to why the corona is so infernally hot. They're not just elegant physics, they're the heartbeat of solar weather. Now imagine something far smaller, a dark, tumbling object from another star system, slicing through that same domain. When 3I Atlas swung inward toward the sun, it didn't just enter a region of radiation and heat. It plunged through a storm of twisting magnetic power. Torsional Alphen waves can carry immense localized energy, enough to jolt the plasma around them into eruptions. If such a wave intersected the object's path, the encounter would be anything but passive. Picture this: the object's surface, laden with volatile ices and metallic inclusions, suddenly bombarded by surges of electromagnetic pressure. Electric currents would dance across its crust. Gas pockets might rupture, propelling jets of vapor that could alter its spin or even its trajectory. For a brief instant, the body would shine brighter, not because of an engine, but because of physics. What some interpreted as intelligent activity could have been the sun itself flexing its magnetic muscles. The numbers support the idea. Based on recent DKS data, the power flux in those twisting fields can reach several thousand watts per square meter. That's roughly the equivalent of parking a spacecraft beneath an arc welder the size of a planet. Volatile materials, carbon monoxide, methane, frozen water would flash into vapor almost instantly. Instruments that later recorded a delayed flare near perihelion may have caught precisely that, the moment an interstellar fragment brushed through a crest of magnetic fury. This possibility doesn't lessen the mystery, it reframes it. Because the sun, in its infinite turbulence, is capable of mimicking the extraordinary. The same burst of heat that looks like ignition could be nothing more than a magnetic handshake. The same twist of plasma that seems to suggest intention could be nature, performing an old routine in a language we're only beginning to understand. And yet, that realization cuts both ways. If our sun can twist energy into invisible knots that radiate power across millions of kilometers, then what about other stars? What of the hyperactive red dwarfs or the young protostars whose magnetic fields dwarf our own? Their alpha waves could carry energies so vast that any object passing nearby would appear to behave unnaturally, accelerating, flaring, or splitting apart. Suddenly, the line between a natural and artificial event dissolves. In the cosmic theatre, physics can wear the mask of design. The irony is beautiful and a little terrifying. The closer we get to explaining the sun, the more we realize how alien it already is. We used to think of it as a stable, predictable furnace. But it is a living magnetic labyrinth, a vast resonant engine of chaos. The corona's heat is no longer a static mystery. It's a song of twisted fields and resonant harmonics. When an interstellar visitor passes through that environment, it becomes part of the melody, even if only for a fleeting measure. There's also a lesson here about our own expectations. Humanity has a habit of reading intention into pattern. We see faces in clouds, gods in thunder, messages in static. When the sun speaks through magnetism, we listen for language. But sometimes the universe is simply loud, and we are standing too close to the speaker. Still, it's hard not to wonder, what if the timing wasn't random? What if the discovery of these waves, confirmed only months before 3I Atlas's closest approach, is itself part of the same cosmic coincidence? The same sun that revealed its hidden knots of energy also swallowed an interstellar messenger in plain sight. Two mysteries orbiting each other, one born of plasma, the other of silence. The sun in this story is both culprit and key. It can explain the heat flare, the brightness anomaly, the supposed telemetry spike. It can even mimic the behavior of something powered, something alive. But it also forces humility. If the ordinary processes of a star can look extraordinary to us, then how many other wonders are we misreading? How many signals are really storms? This is the uncomfortable beauty of modern astronomy. Each new discovery answers one question only by fracturing it into 100 more. The closer we look, the less the universe behaves. The cosmos refuses to simplify itself for our convenience. And perhaps that's why the mystery of 3I Atlas endures. We've found a plausible explanation, but not a comforting one. Because if the sun itself can impersonate intelligence, then maybe intelligence is not as unique as we think. Maybe nature, at its most extreme, already behaves like a mind, self-organizing, recursive, creative in its own right. The universe doesn't need engineers to produce ore, it only needs motion and magnetism. But ore, once awakened, doesn't fade easily. So as 3I Atlas disappears into the glare and re-emerges on the far side, we're left with a question that reaches beyond the data. Did we just witness physics or a performance? That question carries us forward, toward another marvel unfolding light years away, not a mystery of destruction, but of creation. Because even as one object vanishes, another story begins. A story of worlds being born before our eyes. The James Webb Space Telescope has just captured something extraordinary, a moon factory in progress, where dust and gravity sculpt satellites around a forming planet. And in that distant nursery, perhaps we glimpse what 3I Atlas once was, or what it might yet become. Part 12, James Webb's Moon Factory Discovery. In the early months of 2025, humanity witnessed something once thought impossible. The James Webb Space Telescope, with its golden eyes turned toward the Chameleon constellation, captured an image that stunned the astrophysical world, a glowing disk of dust and gas swirling around a young exoplanet called CT Char b. Within that luminous fog, something extraordinary was happening. Moons were being born. Astronomers have long theorized that giant planets, especially those forming far from their host stars, should spawn miniature disks of their own, circumplanetary disks where matter collects, cools and coalesces into moons. We've seen the remnants of such processes around Jupiter and Saturn, their many satellites serving as fossil evidence of a similar birth long ago. But never before had we seen this happening beyond our solar system. The Webb image was the first direct proof, not an artist's impression, not an inference from spectral data, but actual photons travelling for hundreds of light years to paint the portrait of another world in creation. It was like watching time rewind. The scene mirrored what might have occurred in our own neighbourhood 4.5 billion years ago. Dust grains colliding, fusing, snowballing into moonlets that would one day carve orbits of their own. A cosmic maternity ward. A moon factory. The phrase spread through scientific circles and headlines alike, because it captured something both mechanical and miraculous, a universe capable of reproducing its own beauty with assembly line precision. The level of detail Webb achieved was staggering. We're now able to resolve structures only a few light years away with a clarity once reserved for the planets of our own system. Spiral arms of dust, thermal gradients, temperature variations, all mapped in exquisite infrared detail. It's no longer theory, it's observation. For the first time, we aren't guessing how moons form. We're watching it happen. And yet here lies the irony. While we can watch a baby moon forming 100 light years away, we can't fully describe an interstellar object that passed through our own backyard. The cosmic joke writes itself. It's as though technology has outpaced geometry. We can peer across time, but not around the sun. The interstellar visitor 3I Atlas, now lost in the glare of our own star, remains a phantom. We have the tools to image the genesis of alien satellites, yet the closest interstellar artifact in history vanished into daylight, untouchable by our instruments. This paradox reveals something profound about our limitations. Our telescopes are not just marvels of engineering, they're extensions of our biases. The James Webb excels at what is cold, distant, and slow. Its eyes thrive on faint heat in the depths of space. But near the sun, that same brilliance blinds us. The detectors saturate, the optics falter. We can look across galaxies but cannot see what hides behind our own light. If the next generation of telescopes, the Extremely Large Telescope, ELT, in Chile or NASA's conceptual Louvre Observatory, had been operational only a few months earlier, the story of 3I Atlas might have been different. The ELT, with its 39-metre mirror, will soon deliver resolutions high enough to spot exoplanets directly, even in the glare of their parent stars. Louvre, still on the drawing board, would do for interstellar visitors what Webb has done for distant worlds, expose them in spectral detail. Timing, not technology, is our curse. The instruments exist. The cosmos simply didn't wait for us to finish building them. The contrast between Webb's triumph and 3I Atlas's mystery is humbling. On one side, exoplanet science strides into a golden age, graduating from inference to revelation. On the other, interstellar research drifts backward into uncertainty. We used to model comets and asteroids with confidence. Now we chase a ghost that refuses to fit our equations. Webb shows us disks so symmetrical they could be mistaken for engineering. Atlas shows us a silence so deliberate it feels intentional. Between them lies the fragile, shifting boundary of knowledge. Every image Webb sends back expands our understanding but also mocks it. We see structure, but do we understand process? We detect motion, but do we comprehend cause? Even in crystal clarity, mystery endures. The universe hides meaning behind beauty, and every discovery opens a deeper layer of confusion. The closer we get to seeing creation unfold, the less certain we become about the nature of what we see. There's a poetic irony in that. Our most powerful eye in space has shown us how worlds begin, yet the fleeting visitor that passed through our solar system, perhaps carrying stories from another, left us in darkness. Maybe that's the point. Perhaps the cosmos reveals one secret only as it conceals another, maintaining a balance between knowledge and wonder. In this light, Webb's moon factory is more than a scientific triumph. It's a mirror. It shows us both our capability and our blindness. We can gaze upon the birthing of alien moons, but we cannot yet decode the final whispers of an interstellar traveller. We've mastered the art of seeing, but not yet the art of understanding. As new observatories prepare to rise, the ELT, the 30-metre telescope, the Habitable Worlds Observatory, our reach will extend further, our lenses sharper, our exposure deeper. But no instrument, no matter how perfect, can guarantee comprehension. To see is one thing, to know is another. And perhaps that's the quiet message threaded through this era of astronomy. Clarity is not truth. The universe remains an enigma wrapped in light, offering visions that dazzle but rarely explain. In the next part of this unfolding story, vision itself becomes suspect, because the next revolution won't come from glass and mirrors, but from algorithms. Artificial intelligence is beginning to rewrite the way we see the cosmos, teaching our machines to interpret light in ways no human mind can. The eye of the future is not a telescope, it's a mind made of code, and what it sees might change everything we think we know about the universe. Part 13, AI Restores. Web Imagery. The Double-Edged Sword. Artificial intelligence has quietly become the invisible co-author of modern astronomy. Every image of deep space we celebrate today, those stunning portraits of nebulae, galaxies, and exoplanetary disks, has likely passed through the invisible hands of an algorithm. In mid-2025, a new leap arrived. A neural reconstruction system called AMIGO, Adaptive Multi-Inference Gradient Optimizer, developed by a consortium of astrophysicists and computer scientists working across NASA, ESA, and private observatories. Its purpose sounded simple: to denoise, restore, and interpret faint astronomical signals from the James Webb Space Telescope and other deep-field instruments. In practice, it represented a quiet revolution. AMIGO could recover structures hidden beneath cosmic glare, reconstruct lost stars in overexposed regions, and even interpolate missing fragments of dust lanes where sensor data failed. In early tests, it managed to extract faint background galaxies from datasets once thought too corrupted to analyze. To human eyes, its reconstructions looked breathtaking, sharper, deeper, almost too perfect. The problem was, perhaps, that they were too perfect. For the first time, machines were not just processing the universe, they were interpreting it. AMIGO's neural engine didn't merely remove noise, it inferred what the missing information should look like, based on billions of learned patterns from past observations. That meant reality itself, as we saw it, was being filtered through a statistical imagination. It sounds miraculous, and in many cases it truly is. The faintest echoes of the cosmos, once lost to entropy, are being resurrected through pattern recognition. Entire astrophysical phenomena have re-entered the scientific conversation thanks to AI-aided reconstruction. But this new power comes with a philosophical and epistemological weight. If machines are now curating our perception of the cosmos, how do we know what's real? That question took on new urgency with the re-emergence of 3i Atlas. Some of the early fragmentary images rumoured to capture its faint post-perihelion glow were reportedly processed through AI-driven enhancement pipelines, not necessarily AMIGO, but similar systems designed to boost low-light data. Within hours, speculative frames began to circulate through online observatories and data-sharing channels. A slight flicker in brightness became a pulse. A faint asymmetric blur became a trajectory deviation. Algorithms trained to find motion and coherence had filled in the blanks. Here lies the quiet danger. These neural tools are not malicious, they are obedient. They fill gaps according to training data, the archive of everything the machine knows about what stars, comets, and cosmic structures should look like. When the input deviates too far from known patterns, the system improvises, and in that improvisation, bias becomes synthetic physics. The universe bends not because it behaves differently, but because the algorithm expects it to behave the same. Consider a hypothetical. A faint brightness deviation is detected near the sun. The raw telemetry is noisy, scattered photons, turbulent interference from the corona. A neural filter enhances contrast, suppresses noise, and stabilizes the frame. What emerges looks like a pulsing rhythmic signature. To the human eye it seems real, but is it artifact or evidence? Without the unprocessed data, there's no way to know. In the analog era, uncertainty was visible, a grain, a blur, a jagged noise pattern. In the AI era, uncertainty wears a mask of precision. The corrections are plausible, elegant, and entirely synthetic. The algorithm does not confess its guesses. It smooths the jagged edges of ambiguity into seamless certainty. And that, paradoxically, is the most dangerous illusion of all, false confidence. The implications go far beyond 3i Atlas. AI now assists in detecting exoplanets, classifying galaxies, and identifying transient events like supernova and gamma-ray bursts. Neural nets have flagged candidates for technosignatures, potential signs of alien technology, before human astronomers even knew where to look. These discoveries often turn out to be false positives, but the fact remains. Machines are now the first witnesses of the universe. Humans follow. That inversion of hierarchy is unprecedented. For millennia, our instruments extended our senses. Now they interpret them. What we see is no longer the untouched universe, but an AI-curated reality, a reconstructed mosaic of light shaped by layers of statistical inference. The telescope no longer ends with glass, it ends with code. So when the next batch of data from 3i Atlas appears, and the headlines scream of strange oscillations or non-gravitational acceleration, we must ask, are we seeing the cosmos as it is, or as our neural filters imagine it? Transparency in AI pipelines becomes as crucial as the instruments themselves. Every algorithmic decision, every denoising pass, every interpolation must be logged, verified, and open to scrutiny. Otherwise, science risks becoming a belief system again, not in gods or ghosts, but in code we can't explain. And there's another deeper irony. The very success of these systems depends on the assumption of normality, the expectation that the universe behaves as it usually does. But what happens when something truly anomalous appears? When a signal genuinely breaks the mold, the machine may discard it as noise. The extraordinary could be erased before it ever reaches human eyes. The very intelligence we built to help us find the unknown might be filtering it out. This is not paranoia, it's a structural issue. In 2024, a prototype AI anomaly detector used by the SETI Institute mistakenly erased a narrow band signal that didn't match its internal model of a natural transmission. Only later, when reviewing the logs, did researchers realize the potential significance. The event reignited debate about transparency and human oversight. How many discoveries might be hidden, not in the stars, but in the discarded decimals of an algorithmic filter? AI, in its brilliance, has given us vision beyond human limitation, but at the price of interpretation. Every cleaned pixel is both revelation and rewrite. The line between signal and synthesis blurs. The cosmos we now study is no longer raw. It is curated reality, shaped by invisible collaborators that never sleep, never doubt, and never tell us when they're guessing. And perhaps that's the final twist in this story. The universe no longer hides its secrets in darkness, but in data. The frontier is not in the stars, it's in the training sets. The next mystery may not be out there, but in here, inside the logic of our own creation. As 3i Atlas nears visibility once more, astronomers will point their lenses and algorithms skyward. But the question remains, when the light returns, whose eyes will be truly seeing? Ours or the machines? In the next section, we turn to that question directly, exploring how AI is no longer just interpreting the universe, but beginning to predict it, running simulations so complex they may soon tell us what happens next before the sky itself does. Part 14. Oxford and Google Cloud's AI breakthrough in transient detection. In October of 2025, Oxford University, in collaboration with Google Cloud, announced something that quietly redrew the boundary between human and machine astronomy. Their researchers unveiled a neural system capable of classifying transient events, cosmic phenomena that flicker into existence and vanish in seconds, with unprecedented speed and accuracy. Powered by hybrid cloud computing and adaptive inference layers, this AI could process live telescope data and assign probabilistic identities to unknown signals in less time than it takes to blink. For decades, astronomers have relied on distributed human collaboration, scanning sky maps, comparing frames, and waiting hours. or days for consensus. That delay often meant missing the most critical window of observation. The Oxford-Google system changed that. Now, an algorithm can watch the sky in real time, ingest incomplete data, and still make an informed call. Supernova candidate, cometary outburst, solar transient, or the most tantalizing label of all, unidentified phenomenon. The promise is breathtaking. The danger is existential. If such a system had been active during 3I Atlas's perihelion phase, those fateful days when the object slipped behind the sun and the world went blind, it might have caught something no human did. A spike, a flicker, a sudden pattern in light intensity that didn't fit the usual solar noise profile. The AI could have triggered an alert, forcing telescopes to pivot, data streams to synchronize. We might have had a record of the moment when myth became evidence. Or, just as easily, it could have gone the other way, misclassifying a solar flare or coronal arc as a sensor glitch, flagging the event as probable artifact, and discarding the data before a human ever saw it. That's the paradox of automation. Speed without skepticism. When a machine decides something isn't worth investigating, its confidence becomes contagious. Every network downstream trusts the label. Machine certainty, even when wrong, propagates faster than human doubt. In a world where information spreads at the speed of thought, one mistaken tag can rewrite the narrative before the truth catches up. Now imagine that same system connected to social media, a live feed of algorithmic classification visible to the public. A single label, unidentified transient high confidence, leaks from a database, and within minutes the story spreads across every platform. Thousands of posts, millions of interpretations. In the absence of explanation, imagination fills the void. An error becomes a mystery, a glitch becomes a signal. The scientific process was never designed for virality. It was built on patience, peer review, and the slow crawl of certainty. But the intersection of AI, astronomy, and real-time dissemination has changed that forever. Space has become theatre, not in the sense of rockets and exploration, but in the sense of collective psychology. The cosmos is now a mirror, reflecting whatever narratives we project onto it. When 3I Atlas disappeared, people didn't just ask where it went, they asked what they were supposed to believe. Some saw deliberate silence, others divine timing. In an age of algorithmic witnesses, every absence feels intentional, and yet this same system that feeds speculation could also save us. By processing millions of data points a second, AI can detect the subtlest signs of danger, the dimming before a supernova, the asymmetric motion of a near-Earth object, the whisper of a dust-tail inversion that signals instability. A human observer might miss these signs, the AI won't. It doesn't blink, doesn't sleep, doesn't wait for confirmation before sounding an alarm. In this way, the same mechanism that spreads rumour can, paradoxically, preserve truth. The difference lies not in the data, but in transparency. Will these systems show their reasoning? Will they explain why a light curve was classified as unknown? Or will they remain opaque, black boxes outputting cosmic verdicts? Right now, that debate is raging quietly across research circles. Some advocate for explainable AI in astronomy, where each decision is accompanied by a rationale humans can audit. Others argue that interpretability slows performance, and that in emergencies, like asteroid alerts or gamma-ray bursts, speed matters more than explanation. Both sides are right, and both are wrong. The core dilemma is philosophical. Who gets to define reality when the observer is no longer human? We built these systems to extend our senses, but in doing so, we gave them the power to choose what counts as evidence. The telescope used to be an extension of the eye, now it's an extension of the mind. Observation itself has become participatory, recursive, a loop where humans interpret machine interpretations. Every click of data is now a negotiation between perception and prediction. We don't just watch the universe anymore, we co-author it with our machines. When AI flags something as anomaly, it's not only describing the cosmos, it's shaping the next set of human questions, funding priorities, and public fascinations. It decides what we see, and more importantly, what we don't. So as Oxford and Google celebrate their achievement, a system that can identify the transient heartbeat of the universe within seconds, we must remember that speed is not understanding. The AI doesn't wonder what it's seeing, it doesn't feel awe, It doesn't hesitate before declaring the unknown. That hesitation, that fragile gap between knowing and not knowing, is where human curiosity lives and where discovery is born. The future of astronomy will not belong to humans or machines alone, but to the conversation between them. Every alert, every classification, every unknown tag will test not just our technology, but our humility. Because the faster we label the universe, the more we risk missing the moments that refuse to be labelled. And that brings us inevitably to the final question, not of science, but of philosophy. When the sky speaks through algorithms, when discovery happens faster than comprehension, what role does belief play in an age of quantified wonder? The last section will explore that closing paradox, the idea that, in our pursuit to master truth, we may have engineered the perfect illusion of it. Part 15, The New Epistemology of the Sky. We began this journey searching for a comet or a craft or something in between. We wanted data, clarity and closure. Instead, we are left with a mirror. 3i Atlas has become less an object than an idea, a reflection of everything we project into the unknown. When it slipped behind the sun, beyond every sensor and scope, it carried with it our hopes for certainty and returned silence. And in that silence, it exposed something raw, how fragile our relationship with knowledge truly is. For centuries, astronomy has been the purest form of human curiosity, looking outward to understand ourselves. But now, looking is no longer simple. Every observation passes through layers of mediation, digital processing, algorithmic filtering, institutional gatekeeping, and the invisible biases of interpretation. Seeing has become an act of translation. Truth must compete with virality, and certainty must survive attention spans. When 3i Atlas crossed its perihelion, no human eye saw it directly. The decisive moment, the turning point of the entire mystery, happened in absolute silence. And so, we find ourselves not as discoverers, but as witnesses to something that may have already decided what it wanted to reveal. What remains certain? Only fragments. A heat flare that shouldn't have been there. A spike in telemetry data coinciding with the sun's radio interference. A missing hour from multiple observatories' logs, dismissed as instrument recalibration. Beyond these pieces there is only speculation and the endless human instinct to connect the dots, even when the pattern might not exist. Yet perhaps this ambiguity is not a failure. Perhaps it is the new frontier. The history of science is not the history of answers, but of better questions. Each unknown opens a wider field of wonder. We used to think of discovery as revelation, uncovering what is, but maybe it is becoming something else, a negotiation between evidence and humility, between trust and doubt. We are learning that knowledge is not a lens we look through, but a dialogue we hold with the universe. And maybe, just maybe, that is the true message of 3i Atlas. Not a transmission from beyond, but a reflection from within. A cosmic reminder that the pursuit of truth is as much about character as it is about comprehension. Because every time we gaze outward, what we see depends on who we are when we look. In the control rooms and observatories scattered across Earth, from Mauna Kea to the Canary Islands, from Palomar to Paranal, the instruments wait. The software runs its predictions. NASA's dashboards display countdowns. JPL's ephemerides trace possible return arcs, and NOILAB's polarimetry logs highlight the faintest shifts in light polarization, waiting for the object to re-emerge. All of them point to a single window, mid-November 2025. Then, the world will look again. And what will we find? Maybe nothing. Maybe a dim, fading object barely clinging to the margins of visibility, the cosmic equivalent of a whisper lost in solar noise. Or maybe something else, a change in spectrum, an irregular light curve, a trajectory. That doesn't quite match Newton's expectations. If that happens, the debate will ignite again. The same arguments, the same camps, the same impossible hope that somewhere in the data lies the answer to a question we never dared to ask aloud. But even if the mystery deepens, something irreversible has already occurred. Humanity has glimpsed the edge of comprehension and realized that it cannot see beyond it. For all our models and instruments, our quantum precision and machine learning, there remains a veil we cannot pierce, not because the universe hides from us, but because our perception itself has limits. We have reached the border between knowledge and faith, between science and story. Whether 3i Atlas was stone or signal no longer matters. What matters is that we looked, and for the first time, it felt as though the universe looked back. That silence wasn't absence, it was acknowledgement. It was the cosmos reminding us that observation is not a one-way act. We are participants in a conversation too vast to understand. Now, as the world waits for 3i Atlas to reappear, the real story shifts inward. What does it mean to seek understanding in an era when data can be erased, rewritten, or generated synthetically? What does it mean to believe in discovery when algorithms can fabricate evidence more convincingly than nature? The challenge of our time is not how to collect truth, but how to recognize it when we see it. Across social media, theories pulse and collide like particles. Was it a natural body, an artificial probe, a mirror-sailed craft leveraging solar radiation to maneuver? Each interpretation tells us more about our own psyche than about the object itself. In the 21st century, every mystery becomes a reflection of the observer. The cosmos has become our collective Rorschach test, an infinite canvas upon which we project meaning. And perhaps that is how it must be, because wonder, real wonder, can't survive certainty. The moment we define everything, we stop seeking. 3i Atlas may never deliver an answer, but it has already fulfilled its purpose by reviving the one thing we risk losing in an age of algorithms. Or, the true shift has already happened. We've moved from explorers of space to interpreters of perspective. The frontier is no longer out there, it's within us, in the way we process the unknown. The old question, what is it, has become, what does it mean that we don't know? That transition is not just scientific, it's existential. So now we wait. Not as scientists, but as witnesses. Not for discovery, but for confirmation that discovery still means something in an age where mystery itself feels endangered. When the next glint of light emerges from behind the sun, telescopes will pivot, servers will hum, and once again humanity will hold its breath. But the real revelation will not come from the data, it will come from the realization that we are still capable of wonder, because the next light we see may not only reveal the fate of 3i Atlas, it may reveal what kind of species we have become, one that demands proof before it dares to believe, or one that learns to live gracefully with the unknown. And somewhere beyond the sun, whatever decision was made, whether by rock, radiation or reason, is already on its way here. The echo of that silent crossing travels still, a message without words, carried on the light we have yet to receive. When it arrives, it may change nothing, or it may change everything, but either way the universe will have spoken not through answers but through absence. And we, for the first time in a very long time, will be reminded that not knowing is the beginning of all wisdom.